So those of you who are checking in remotely, because there aren't all that many of you here in person, the midterm is tomorrow. The midterm content is explained on the syllabus. It is also explained on the updated rough schedule, what is going to be covered. That's the stuff that we covered up to the beginning of last week. The midterm is going to be long answer only. We do not know exactly how many questions are going to be on the midterm yet. We haven't finalized it yet. I never finalized it till right before because I never teach to the midterm. You will be able to go back and forwards on it. It will be posted on Blackboard. You will need to post individual images and upload them to individual questions. That's, I think, all I'm going to say about the midterm. So we've covered stereochemistry, we've covered naming of these things, we've covered how to do RNS, we've talked about Newton projections, we've talked about confirmations the last few weeks. We are going to be circling back on some of these concepts, but we're kind of at this point now, you have the toolkit. We've covered kind of the intro to the entire course. So until here, in some ways, a lot of this would have been review for some people. For some people, I think this is new material at this point, and you've run into new material already. For others of you, you will have seen all of this before. Now we're actually switching into the chemistry part of organic chemistry, where we're sort of looking at change and we're looking at reactions. To this point, we can kind of talk about structure and physics. Now we're switching over to talk about chemistry. So this is not about chirality. Today we're going to be, I'll update this title slide. Today we're going to be starting to talk about carbonyl chemistry. You know what? So Day, I just asked, can you do a practice midterm assignment on Blackboard so we can see how the uploading process is? Yeah, I will. I'll post something so you can practice on that tonight or tomorrow morning before the exam. That's a fair question. I will make sure we do that. It will probably be something like upload pictures of your cat or your dog or your goldfish or hamster or the squirrel that lives outside your house. We had one graduate student who came here in early October and was in quarantine for 2 weeks in a very small apartment and was posting updates of pictures of the squirrels outside her place on a seemingly hourly basis. So anyways, you can practice uploading figures, and they're going to be pictures. That's what you're going to be uploading. And that's what we're going to be evaluating and marking because we want to be as simple as possible. Okay. If you've been following the schedule, probably we're going to get a little bit ahead of ourselves here because I'm sure most of you are both focused on the midterm. What, screw it, I'll deal with whatever we're going to talk about in this class after the midterm. I'm not going to worry about it now. Yeah, PDFs will also upload. I'll accept Word files, PowerPoint files, various forms of image files, PNGs, JPEGs, TIFFs, bitmaps, PDFs, Word files, PowerPoint. I'm not accepting shit that we can't open using PC, so no pages. It won't accept that because that's a stupid format. And none of that Apple's proprietary image format, I can't remember what it's called. Can't use that either. Okay. If you can upload a stone tablet, you're welcome to. It is difficult. It is difficult to upload stone tablets or smoke signals. Normally, we need to upload images of smoke signals and stone tablets. But if you want to throw a stone tablet at the internet and I can get a copy of it, then that's okay. But it's really slow writing in stone. I don't recommend it. So what we're starting with is carbonyl chemistry. And again, carbonyls, it's a fancy word for C double bond O. That's it. It says that can we upload a screenshot from an iPad? You might need to convert it. It depends how iPad saves screenshots. But yes, you can. You just might need to convert it to a different file format. But you can do that using basically any piece of software that can open the image. You can save as something else. we're just trying to make sure that the GAs who are trying to mark this thing can actually open your file. And if we can't open your file, we're giving you a 0. And won't accept files that we can't open. So you're responsible for uploading non-corrupted files. Just like if this was a paper exam, you'd be responsible for handing in the paper and making sure that you weren't handing in like shredded stuff. Okay, so carbonyl, it's a C-double bond O. What we're talking about today is additions to carbonyls. Okay, screenshots and iPads are JPEGs, that's fine. JPEGs are going to be perfectly acceptable. So yeah, if you want to use iPads, go nuts. Screenshots on my Android are all JPEGs as well. And on my tablet are PNGs, I think, which is fine too. Okay, that's a good question too, Hope. So Hope says, I said it's a 3-hour midterm with a 4-hour period. Can we take all 4 hours or only 3 hours once we start? There's no time limit on it. So it's a 3-hour midterm. I'm giving you 4 hours. You can use all 4 hours. I'm not saying, okay, you only have 3 hours. You have 4 hours to do a 3-hour midterm. I just said that, Ahmed, that yes, I am. Thanks, Drake. No, what will happen is at 4 o'clock, if you do not have accommodations that give you extra time, the exam will shut down and what you have uploaded will be marked. Anything you haven't uploaded will not be marked. And desperate emails saying, but I haven't uploaded everything, will be met with stony silence. So I strongly recommend, and I'm going to send this out as an email and it'll be at the front of the exam. I will have zero sympathy. It's like, well, I did all the questions. I wasn't uploading. Upload as you go if you're sure about your answer. If you're not sure about your answer, just give yourself time. It's a 3-hour exam. I said I'm going to write for slightly under 3 hours compared to normal. It's going to be slightly shorter than normal. You have 4 hours. I have zero sympathy for I didn't have enough time to upload this. You have an hour to upload the exam. And if you can't upload, 10 images in an hour, I don't know what to say. I will be available on Teams on this channel during the exam. It's going to be slightly shorter than older midterms, Shauna. But again, it's a midterm. Standard ways of writing tests. And I know this is unfair. Some of you have learned how to write tests, and some of you have not really been taught how to write tests. The clue is take a look at the entire test, answer the questions that are easy for you first, then answer the questions that are increasingly hard. Don't get overly bogged down on a question, spending all your time on it. Like timed examinations, time is one of the factors that is used. So and for some of you going like, yeah, of course, I know that. That's exactly how you do it. And I can say that every year I see people who write the beginning of the exam and then they have no answers for later questions in the exam, even though later questions in the exam might have been easier for them and they struggle to answer some of the early questions. So they just don't move on. If you get stuck, move on. Anyways, carbonyls, C-double bond O. We were talking about this a lot. There is a resonance structure for carbonyls that looks like this. So this actually brings rise to, it's almost, I'm qualifying myself. I don't think I need to. I think I can say this. It is a truism in organic chemistry that molecules almost always react from the form of their second most stable resonance structure. And I don't I'm sure there are exceptions to this rule, which is why I have the almost always. I can't think of any. And I doubt we're going to come across any. So whenever we're looking at a molecule and a carbonyl, and you're thinking, what the hell is that going to do? The second most stable resonance structure almost always highlights the largest and most important charge differentiation in a molecule. And what we're going to realize is that for the most part, until the very last couple of courses in this course, we're going to be talking about ionic chemistry. And ionic chemistry is the chemistry of ions. And so what we're going to be doing is moving 2 electrons at a time. We're going to react negative charges with positive charges. And it's because negative charges like positive charges. And negative charges are electrons, and positive charges are nuclei. And so we're going to use electrons to target nuclei. And I am waving my hands around, and I do not have my camera on, so you're missing this fine performance. So what we're really going to always be considering and thinking about is where do the negative charges want to go, and how do we get rid of the positive charges? Because that's how chemistry works. Charges want to interact. We spent a lot of time talking about charges. We've spent a lot of time talking about the stability of charges. Now we're going to see why all that shit matters. So why does ranking resonance structures matter? Well, because they often react like their second most stable resonance form. So carbonyls react like this. The oxygen is nucleophilic. What does that mean? We're going to talk about that in a second. The positive charge here is electrophilic. So these are terms I am going to use a lot. Nucleophilic means likes nuclei. Electron rich. Is electron rich. The nuclei are not electron rich. The nucleophile is electron rich. This also means arrows start here. Because we were talking about this with the acid and bases, we're going to get more practice here, but arrows in organic chemistry, reaction arrows, like the arrows that show the movement of electrons and things, well, they show the movement of electrons. So they begin at the electrons and they go to the place where the electrons are going. So arrows start at nucleophiles like nuclei. Electrophilic centers. This means they like electrons. And they are often electron deficient. So they're short on electrons. That's it, really. We're just going to iterate this, and we're going to start seeing patterns in the way that things react. But carbonyls rely on the fact that the carbon is electrophilic and the oxygen is nucleophilic. And that's really it. So what I want to talk about is maybe the simplest reaction we can draw in, no, maybe not the simplest. It's awfully freaking simple. So let's say we have formaldehyde. And I'm going to talk about some conventions here. Okay, so there's a bunch of new concepts in this thing I have just drawn. What I've drawn is a reaction arrow. What that means is we have starting materials on the left, we have products on the right. On the arrow, what we normally have are things called reagents above the arrow. Generally, not always the case, but often if you're reading these things, you'll see reagents above the arrow. Reagents are things that are going to be involved in the mechanism. They're things that are going to be involved in a reaction. They're going to play an active role. We might call this the reactant because it is the thing which is reacted upon by the reagent. There is a very squishy area of differentiation between the terms reagent and reactant. They can be used interchangeably. I would be okay if you refer to this methyl lithium as a reactant instead of as a reagent. I think I would prefer that the formaldehyde get called a reactant, but again, it wouldn't be wrong to call it a reagent. We're converting one thing to another thing, and they're reacting together. So stuff above the arrow acts as if it's on the left-hand side of the arrow. Remember when we had acids and bases, we had an equilibrium arrow, we had something on the left, we had something on the right. There was nothing over the arrow. In this case, when we have an arrow like this, things over the arrow are treated as if they're on the left-hand side of that arrow. We just don't write it that way because I don't know. This takes up less space. I do not know where these conventions come from. Below the arrow, we often have conditions, the reaction conditions. So here we have THF is a solvent. It means tetrahydrofuran. You do not need to memorize this. When we start doing a lot of chemistry, I'll give you cheat sheets on all the acronyms that we're using for this stuff because it's probably good to memorize some of them. Okay, let me correct that. It's good to memorize them, but memorizing shit doesn't have a lot of pedagogical purpose. I think it's fine if you look it up. You're going to be faster if you have a few of these at your fingertips. And then we also have the temperature. This tells us a bit about how the reaction is occurring. Sometimes you also have concentration down there, like how concentrated the reaction is. You'll sometimes have reaction times under there. Is it half an hour, an hour? So conditions often get put under the arrow. Reagents are put over the arrow. And then the product is drawn on the right-hand side of the arrow. In this case, our product, immediate product, is going to be this. You know what, I'll be consistent. Just so we can identify the methyl and the lithium. So this is how I would write out a reaction. I am saying the thing in red on the left, using the stuff through the conditions explained by the stuff over and under the arrow, becomes the thing in right in purple on the right. So this is a reaction scheme. The scheme doesn't give us a lot of information. It doesn't give us detail, but it tells us this goes to this under these conditions. So what we want to do now is we want to talk about mechanism. So a reaction scheme is what is happening. A mechanism is how things work.
Dr. Trant, what about the hydrogens?
On here? Oh, shit. I thought I was working with acetone. You're absolutely right. Yes, I'm very sorry. I am a moron. Yeah, you're absolutely right. Thank you, Dina and Julia. I had no idea what you were talking about, and I just skipped over it. Yeah, they're there. They didn't go anywhere. So a reaction scheme is what happens. A reaction mechanism. If I can get my tablet to cooperate, is how things work. And so here, when we draw a mechanism, what I want to see is I want to see how the electrons move. So how do the electrons move in this case? So we had our formaldehyde starting material. We had our CH3 lithium. I'm going to write that a little bit differently. How I wrote that is perfectly correct, but let's just do it there so it's really clear that the lithium is attached to the carbon. If I asked you to draw the Lewis dot structure of that, hopefully you would draw the lithium attached to the carbon and not to a hydrogen, even if I wrote Ch3 lithium. And then there was THF. Okay, so what we need to do here is we need to think about a few things. There's a lot of complexity here. First of all, as I said, things react from their second most stable resonance structure. Let's just consider that. You can do this automatically in your mind. You don't need to actually draw this out. Maybe your mind just goes, yeah, it's a carbonyl, O minus, C plus. I know how this works. If you don't need to draw it out, awesome. You never need to. Unless I explicitly ask you to draw it, and I won't. I reserve the right to maybe do it, but I've never done it before, and I don't. Old dogs, new tricks, all that. The second thing we need to realize is, okay, that's how that's polarized. That's great, but for a reaction to occur, you need 2 to tango, so you need the other guy to do something. And right now I've got CH3 and lithium attached together. So if we go back to our electronegativity lecture that I didn't teach, how is that bond polarized? Is the bond polarized, first of all? The carbon-lithium bond? Or is it neutral? You know, everyone's pulling equally. So I'm talking about this. Is the carbon more positive or the lithium more positive? Or is that bond basically like a carbon-carbon bond perfectly equally pulled by both the lithium and the carbon? So we got 2 answers and they contradict each other. Perfect. So there's 2 ways. So oops, exactly. So there's 2 ways to look at this. Remember, you can look at a periodic table and go, as you go right across the periodic table, stuff gets more electronegative. Lithium is in the far left-hand column and carbon's not. So carbon's pulling the electrons towards it. We've been talking always about everything's been more electronegative than carbon because so far we've been comparing everything to carbon. But carbon is a lot more electronegative than lithium. Lithium's about the least electronegative atom out there, like its column is the worst, right? So if we're thinking about how this is polarized, delta minus, delta plus. And I would argue that that bond is ionic. You actually have a C minus and a lithium plus. But in THF, they're probably still associated because it doesn't dissociate them great. But anyways, if you wrote C minus lithium plus, that would be perfectly correct. So what we have here is we have a C minus lithium plus and we have a C plus O minus. And for chemistry to occur, one of these guys has got to be stupid unhappy. Because, you know, the formaldehyde's floating around with other molecules of formaldehyde, and all of them are, you know, this plus minus thing, but they don't do anything. They stay formaldehyde. So we need some molecule, we need a charge to be really unhappy and really unstable. And a C minus charge is really unstable. Methyl lithium, you show it water and it explodes and catches fire. So, and it's because it's just really reactive. The C does not want to be negatively charged. And so what we essentially have and of course we have a lone pair on carbon that is in an sp3 orbital because that carbon is sp3 hybridized, because there's no reason for it to have anything in a p orbital because that's high energy, it's not making any double bonds. And what we're going to do is we're going to use the lone pair electrons, and we are going to point them towards the electrophilic carbon, or the atom that wants electrons. So the negatively charged methyl group here is our nucleophile. This is our electrophile. Now, these are relative terms. Like relatives. Like somebody is your cousin only when they are your cousin, right? They're their father's daughter or son. They are your cousin. So you're comparing things relative to something else. So in this case, formaldehyde is an electrophile when methyl lithium is present because the methyl lithium is acting as a nucleophile. It's the role they are taking on. It's not like an inherent nature of the molecule. But in this reaction, the methyl group is a nucleophile, the formaldehyde is an electrophile. And so if we follow that arrow through from that resonance structure, what we're left with is we've made a new carbon-carbon bond. And we have an O-. Now, O- isn't bad. You know, we've seen a lot of them. They're kind of okay. We have some lithium plus around. It makes sense that we can get rid of the charge and have, now this guy's acting as the nucleophile. It was the electrophile. Now it's acting as the nucleophile. The lithium plus is acting as the electrophile. And we get our product, our immediate product. Notice that this is uncharged. Almost all the time, your product should be uncharged. If your molecule is charged, you're not done yet. It's really hard to like pick up a charged molecule and hold it in your hand. Like this plastic I'm holding, all the molecules in here are uncharged. So this is a mechanism. I have drawn arrows showing how the electrons flow to create the product. Now I drew them on the resonance structure. I could have equally have drawn them on the other thing, not the resonance structure. And if I'd done that, and this is maybe the more typical way of doing it. Sorry, I am really belaboring this example, but I'm trying to show that there are multiple ways that we can sort of represent this. I can also have drawn it like this. And I can draw two arrows at once. It means essentially the same thing as what I did previously. I'm not drawing that resonance structure. By essentially, I mean, it means identical to what I drew previously. And it is perfectly acceptable for you to draw that, not redraw the lithium plus, but kind of use the one that's present on your piece of paper to give us the product. This is also exactly the same thing. And if I asked you what was the mechanism of this reaction, you drew either this answer, the one I drew on the previous page, completely full marks. There is no difference between them. Mohammed, I'm not sure. That question was asked at 1:53, so I think we might have gotten there. What we're doing here is, so maybe Mohammed's question actually is a really good one. So he's like, okay, but why'd you choose to use the methyl group to attack the carbon and not the oxygen to attack the lithium? It's there, I just didn't write CH3, but a straight line works. Because I'm trying to react the most unstable thing in solution. Lithium plus, that's lithium's natural state. Lithium wants to be lithium plus. It's really happy being lithium plus. Actually, we're going to see examples later this course when if lithium is neutral, it gives up electrons readily to become lithium plus. It really wants to be lithium plus. O- is kind of stable. It's the CH3-. It's the most unstable charge in the entire thing that is driving the reaction. And that is always true. The most unstable charge present drives your reactivity because you try and minimize energy. Molecules are lazy, unstable charges are high energy. We want to get them as low energy as fast as possible. So always deal with the most unstable things first. Again, Madison made a great point. Don't forget about the methyl group. Just remember that drawing CH3 at the end of a chain is redundant. I can just draw a stick and it means there's a CH3 at the end. So those are equivalent representations. Okay. So what we're starting with, this is kind of a new addition to the course this year because some students, they take this course and they're not really going to take any more organic chemistry and they're going to write MCATs, and we want to make sure we talk about carbonyl chemistry, which is what we're doing here. So normally I don't discuss, trying this out this year, normally don't discuss a lot of carbonyl chemistry in this course. It's also there from the videos from last year. I'm going to talk about another reaction, which I'm sorry, this one is actually going to add a little bit of complications. This is called a Grignard reaction. I am so sorry about the names I am going to throw with you for reactions. I promise I will never ask you to name a reaction. They are named after people who discovered them. This one's kind of unique because it's actually named after a grad student, but because normally they get named after the boss, even if the boss never actually stepped foot in the lab and had no input into anything, but they get all the credit because life is unfair. But this one is actually named after the grad student. I suck at remembering names. It's kind of nice that I have your names underneath your pictures here, because if we're in class, I'd be screwing up whose hand was going up and I would mess up all your names. I couldn't remember them. I'm really bad at it. But so I think that remembering names of reactions isn't particularly important. I will use short form in lectures, but on an exam, I will always give you the reagents so that you can work it out. So if you remember the name, great. Awesome, good for you. You have a shortcut. And if you don't, you can figure out what to do. So the Grignard reaction is very similar to what we just saw. And it's got a minor difference from that last reaction. I'm going to talk about that. But let's say we had acetone. So I'm going to sketch in a little bit different. So we have the methyl groups there. For a Grignard, what we do is we take magnesium metal. That 0 up there means it's not positively charged or negatively charged, it's magnesium. And we take alkyl bromide. Alkyl means any carbon chain. I am going to specify CH3 bromide. And I'm going to use diethyl ether. And do it cold. Now, this is one of those things where you're looking at this and hopefully you're going, I don't know what the fuck is going to go on. The last one I went, okay, there's a CH3 lithium bond, really, really polarized. I know it's kind of ionic. It's like having a negative charged carbon and a positively charged lithium. We have a really unhappy charge. We can get something to go. Here I'm looking at going, that acetone looks pretty stable. Methyl bromide, I can tell you that carbon halogen bonds, carbon bromine, carbon iodine bonds are weak. And we're going to see how weak later, but they're not stupid weak. I can buy a bottle of methyl bromide and store it indefinitely and nothing's going to go wrong with it. And magnesium metal, you know, you can store magnesium metal on your shelf endlessly. So none of these are obviously highly reactive. None of these are obvious starting places to start the reaction. And this is where we need to take advantage of the fact that just because something isn't reactive on its own, when it's partnered with specific molecules, weird things can happen. So what's going to happen here, our reaction scheme. So we'll start with the scheme. Is going to give us this. Whoa, okay, so now like the magnesium is attached to the oxygen and the bromine, and the methyl group's attached to the carbon. Okay, well that's the pattern I just saw above. And the way we got that, right, was we had a negatively charged carbon. because we know that this carbon here is positively charged, so we want to make a negatively charged methyl. But that's not how this bond's polarized, right? This bond is polarized like that, because bromine is more electronegative than carbon. So what is going on here? What's going on is something kind of weird. I'm introducing this concept here. I understand this is a shitty place to introduce this concept on our first lecture of drawing mechanisms. So we're not going to focus too much on this. We're going to come back to this guy later. We're going to focus on the simple second part of the mechanism. But what's actually happening here is you have a CH3 bromine bond. You have magnesium metal. And we can think of what's happening is the electrons in the bond are attacking the magnesium. If we do that, note I'm putting something in brackets. Brackets means don't take me seriously. This doesn't actually exist. Because it all happens at once. I'm drawing it stepwise, and it's weird and it's wrong, but it's not wrong at the same time because things are complex. So we're not going to worry. I'm going to write, don't worry about this part yet, because it's weird. What I want to focus on down here is what we get. This is called your Grignard reagent. And you'll notice what we've done is we've inserted a magnesium atom in the carbon-bromine bond, and now there's a magnesium in there. And now if we think about how that carbon is polarized. Magnesium, and if you take a look in your periodic table, you'll see that magnesium is to the left of carbon. So we've got that. And now we have a situation that is really similar to the one that we had in the last slide with the methyl lithium. It's essentially identical. And by essentially identical, I mean spot the difference between these two images kind of thing. I mean, they're the same. So we're going to use the electrons in the methyl magnesium bond. It would be okay if you wrote that as CH3 minus magnesium Br plus right next to it. I'll accept that, although I'm less happy to accept it than I would have with the methyl lithium because this is kind of pseudo covalent. That leaves us with MgBr plus. This is why being able to do all those counting electrons and Lewis structures matter, because you need to keep track of the charges. If the electrons went with the methyl group, that left the magnesium as positively charged. And we attack the magnesium. Nor, I just saw your comment, and I don't know what it's in relevance to. Bromine is not going to do anything more at this point. It's going to be stuck on the magnesium. Magnesium bromine bonds are actually really, really strong, strangely. So you're going to make a lot of you're actually going to end up making magnesium bromide in this reaction. But that errors towards inorganic chemistry, and I'll leave it to those weirdos. We love our inorganic chemistry colleagues. So what we've seen here is a pattern where we have nucleophilic molecules attacking electrophilic carbonyls. Another example I want to show on this. Let's change the carbonyl a bit. Now I've gone from a ketone to an aldehyde. And I'm going to use a reducing agent. Lithium, aluminum, hydride. It's neutral. So if you take a moment and you take a gander at your periodic table, you'll see that aluminum is directly below boron, and that's 1 over from carbon. We know that lithium always wants to basically be 1+, so that means that aluminum hydride is negatively charged. How will we draw a Lewis structure of that? We would draw it like that. So let's take a look at this guy for a moment. It's negatively charged, but there's no lone pair. It's a little weird. It's got 8 electrons around it, which is good. So so it wants 8 electrons, which is good, but it's negatively charged, which is bad. And so what we have is we kind of have a resonance structure. I'm going to call this sigma resonance. So all the resonance we've drawn so far has been true resonance with pi bonds and moving p electrons and p orbitals around. This lecture is supposed to be a little bit overwhelming. We're going to do some more problem solving next week once you catch up and you start take a look, and then we get some questions. But I'm just assuming nobody has any questions right now because everyone's focusing on the midterm and nobody's looked at this stuff yet. But we can also think of things in terms of let's just break bonds and see how charges are polarized. It's not really resonance, but it is called sigma resonance. And in this case, what we'd have is we'd have a neutral aluminum, which is great. But now it only has 6 electrons. So it's not super happy. This is actually aluminum, and we'll see it a lot with boron later. They're a major problem. Everything we've seen so far, carbon, oxygen, nitrogen, fluorine, want 8 electrons, and if they're 8 electrons, they can be stable, and that's great. And that's because carbon's got 4 electrons, and everyone else has got more. Boron's only got 3 electrons. So if it's neutral, it's making 3 bonds, but that means it only has 6 electrons around it, but it wants its full octet, so it gets 8 electrons, but that means it's negative, and it's not happy if it's negative, so it wants to go back to 6 electrons, but then it doesn't have its full octet, so it wants to go back to 8 electrons, but then it's negative, and it doesn't want to be negative, so it wants to go back to 6 electrons. You can see why this makes the life of these of boron and aluminum kind of complex. And that's what we're seeing here, is that what this aluminum thingy is a source of H-. So just like lithium CH3 was a source of CH3-, lithium aluminum hydride is a source of H-. So when we had the CH3- in the last lecture, or the last part of this course, or the last slide or two, what we saw was it attacked the carbonyl. It's the same thing again here. Note it's exactly the same arrow I am using. Exactly the same pair of arrows I am using. I'm just going to mute whoever it is who's giving us a lot of background sound. I actually don't know who it is. It was like a microwave or something. Oh, they muted themselves. Okay, it's all good. Let's just draw one of these in. Let's just draw this in a different color, just so we can see that's come in here. So we've added this H- to the carbonyl to generate this species. This then can react with the lithium plus that's around, because there she is. So again, what happened here was we looked for the most unstable thing around here, and it's not really clear what that is. But normally your organic starting material is kind of boring and kind of stable. The stuff under the arrow is your solvent. It doesn't normally participate. So the unstable thing must have been something going on with this guy up here. And it's not clear what that is until you start parsing it and you go, what is that? Well, it's lithium plus, because lithium is almost always plus, which means there's a negative charge on AlH4. And you look and go, okay, Al is underneath boron. It wants to make 6. It only wants to have 3 electrons or 3 bonds. 6, yes, 3 electrons or 3 bonds. It's got 8 electrons and 4 bonds. It doesn't want that, so it's going to release an H-. H- is a nucleophile because it's negatively charged. It attacks our electrophilic carbon the same way everything else has so far, and we make a new hydrogen-carbon bond. These two things I've just drawn here, the carbon attacking or the hydrogen attacking, are essentially the same thing. They are nucleophile electrophile reactions onto carbonyls. But because we're weird, we define them differently. We call this a reduction. And if you remember, Leo the lion says Gur, loss of electrons is oxidation, gain of electrons is reduction. You can also define that as loss of bonds to increase of bonds to oxygen. It's like the organic chemistry definition. Or to be honest, any heteroatom. Again, a heteroatom is anything that's not carbon or hydrogen. Whereas a reduction is increasing the bonds to hydrogen. We don't call what we had up there, we increase the bonds to carbon, we don't call that a reduction. Even though you decrease the number of bonds to oxygen, which you think would, but we just don't, because I don't have a fucking clue. I don't know. But reduction is all about increasing the number of bonds to hydrogen on a carbon. And oxidation is increasing the number of bonds on a carbon to heteroatoms. So if you had 2 and then you go to 3, so you go from an aldehyde to an acid, that's an oxidation. If you go from an aldehyde to an alcohol, and you added a carbon, it's not considered a reduction. If you added a hydrogen, it is. But you've reduced the oxidation state of the carbon, and it's just terminology, and it's a nightmare. What I want to take away from today's class, yeah, there's so Mohammed had some points here. So we are leaving the lithium OHC and the aluminum H3 alone. Yes, we're going to come back to what to do with these. We're going to talk about workups next class, because we're not actually done. These aren't super stable. They are salts. They're fine. But yeah, this is what it is. And Mohammed says also there's an empty bond on aluminum like boron. Yes, there is. It's directly below boron. Aluminum has just an empty orbital. The aluminum has an empty p orbital. This guy is going to be, with the caveat that it's got d orbitals, and so I'm lying to you a little bit. Forgive me. This guy is going to be sp2 hybridized with an empty p. Why? Because if it was sp3, we'd have 4 equivalent orbitals. One of them would be empty. The other ones would all be higher in energy. If it's sp2 hybridized, all our orbitals can be lower in energy because sp2 is lower than sp3. And we have an empty p orbital, which is higher in energy than the sp2s or than the sp3. But who cares? It's empty. So this guy's sp2. This guy's sp3. Again, the hybridization is all about getting to the minimum energy you need to do, because electrons are lazy. Everything is just so freaking lazy. Everything wants to be the lowest energy it can be. This discussion of hybridization of aluminum and boron does not matter. If it helps you, great. If it doesn't help you, forget I ever said it. So we're at 220. Aluminum lost electrons, but it was negative. Now it's neutral. I know it makes me uncomfortable looking at something with 3 bonds too, Aurora, and say it's neutral, but it's neutral. Because it was, if you counted, it was sharing 2 electrons here, so it got to count for 1, and it was negative, and then now it's kind of lost all those, and now it's neutral. I don't like it either. I get a little squeamish looking at it. I am not answering questions about the midterm material at this point, because we're within 24 hours of the midterm. I have a strict rule cutoff on this, Amanda, so no, I am not answering any questions about this after class. Sorry. It's in the syllabus. It's really clear about this, and yeah. Yeah, no. So Clara, there were stuff on because the midterms fall on different points in different years. I don't think I've ever had a midterm this early because we almost started like a week late, right? So, and normally I have midterms a little bit later. So the midterms that are posted have stuff that we haven't covered yet. Like all this stuff we're talking about today, this is not on the midterm. The midterm ended at defining enantiomers and diastereomers, not even naming them. The RS stuff that we covered this week is not on the midterm. So yeah, any chemistry, reactions, mechanisms and stuff that isn't acid-based stuff, because we covered that earlier, is not on the midterm. Yeah. Molecular orbital stuff is fair game. It was covered. So I'm going to leave that here. Yeah, no, and what I would say is if you've been practicing the assignments and doing that, I know a lot of you guys are really nervous. I get that. I completely understand. It's nerve-wracking. It's freaking terrifying. This midterm is going to be easier than the assignments. And I regret some questions I've asked on previous midterms because they were harder than I expected. So good luck on the exam, everyone. Remember, this midterm is almost practice. If you do better on the final, your midterm mark disappears. Your final mark replaces your midterm mark. So this is a learning experience. Like, do the best you can, right? You don't, if you get a 90 on this, then, or 95 or 100, whatever your level is, then, you know, pressure off. But the this is sort of a practice, just a practice with stakes. Okay, have a great weekend, especially after the midterm. I imagine you don't have a great next 20 to 24 hours or so. Amanda, yes, I will answer your email. I'll check it up and check on that. That is fair. That's absolutely fair. Okay. I'll go dig it up right after class. Take care, everybody. If you already sent me an email and you didn't get a response, and it arrived 24 hours before the midterm cut, so before noon today, and you didn't get a response from me, resend me the email. I try and keep track, but I get about 300 emails a day, and I do have things to do other than answering emails, and so sometimes they get lost if a lot come in at once. So I'm sorry if it's fallen through the cracks. I do owe it to you. Okay, take care. Bye.